In this lecture, we will discuss about electrophoresis. So, electrophoresis is deals with the phenomena of motion of charged particles in a liquid under the effect of an external electric field. And this electrophoresis is widely used for separation of charged particles or charged ions from a mixture of these ions by applying an external electric field, and this separation is enabled because these charged particles, they move at differential velocities under the effect of an applied electric field, and the velocity or the speed of the ions is proportional to the electric field, and the proportionality constant differs from one charged species or ion or the other. And based on this differential mobility, if you have a mixture of sample ions, you can separate them and analyze and quantify what is the amount of those sample ions. So in this lecture, we'll focus on how we can derive a relation between the speed of the ion and an applied electric field, and we'll see on what factors does this mobility actually depend. Now, for a particle, we have already seen that for a charged particle, in an insulating liquid, the mobility can be obtained by balancing the drag force and the Coulombic force. So if you consider a spherical particle of radius a, then the drag force is given by 6 pi eta a times the velocity of this particle with respect to stationary fluid. And if you balance this with the Coulombic force, so let's say you have charge Q on this particle and you apply an external electric field E, then the drag force equated with the Coulombic force gives the velocity, which is Q over 6 pi eta A times the electric field. So in an insulating liquid, the mobility is given by this quantity, that is Q over 6 pi eta A. But most of the time we are interested in separating particles or charged ions in an electrolyte solution. So we need to see that what happens if you have this charged particle within an electrolyte solution, and the situation differs from the case of insulating liquid when we have an electrolyte solution within which the particle is immersed. Because now you have these mobile ions in the electrolyte solution which can be attracted or repelled due to the charge on this particle, and that will affect the mobility. Now we've already seen that on a charged surface there is a formation of an electrical double layer, and to understand how a particle immersed in an electrolyte solution behaves under an applied electric field, we'll look at two limiting cases. The first limiting case that we look at is for thick electrical double layers. That means your particle size is significantly smaller than the double layer thickness or the Debye length, that is lambda d. And next case we look at thin EDL, where the particle size is significantly larger than the Debye length, or the Debye length is significantly smaller than the particle radius. Now let's look at this thick EDL case first. So it turns out that the thick EDL case is similar to the case of a charged particle and in an insulating liquid. Okay, and that's because when the EDL is you can consider in EDL to be infinite thickness, then the particle behaves as if it is isolated, and therefore the mobility in this case is same as the mobility of the particle, an isolated particle in an insulating liquid. Most of the small ions, such as let's say sodium, potassium, chloride ions, have really small size compared with the EDL thickness at that particular concentration. So typical concentrations would be some millimolar. Now the bare ionic radius of these ions A is about 0.05 nanometers, but within an aqueous solution, so you don't have this bare radius of these ions. What we have is an hydrated radius, and this is because in aqueous solutions water molecules accumulate one atomic layer of molecules over the ions. So the typical hydrated radius, which we will use for our calculations, is about 0.2 nanometers. So you will see that the typical EDL thickness is about 10 nanometers, so we are one order smaller radius than the EDL thickness, so we can use the thick EDL assumption. Now if we calculate the mobility based on this simple model, what we get is that, let's say we want to calculate mobility of a ion with a unit charge or unit valence. So in that case the charge is equal to charge on an electron, and if we plug in these values, so we have 1.6 into 10 to power minus 19 coulombs is the charge, and we have 6 pi, the viscosity is 10 to power minus 3 in SI units, and the radius is 0.2 nanometers. So if we do this calculation, we will get a value of 4 into 10 to power minus 8, and the units of mobility is meter squared volt inverse second inverse, because if you multiply this with electric field, which has units of volts per meter, you will get meters per second, velocity in meters per second. Now surprisingly, this value agrees pretty well with the measured values of mobility. And note that mobility is a signed quantity. That means if you have a positive charge, mobility will be positive. If you have a negative charge, it will move in the opposite direction to the applied electric field, so it will have a negative value of mobility. Now let's look at the typical values of mobilities of small ions. So what we have obtained from the model is 4 into 10 to the power minus 8 in SI units. So the measured value of sodium mobility is 5 into 10 to the power minus 8, potassium is 7 into 10 to the power minus 8, and chloride is minus 7.9 into 10 to the power minus 8. So at least till an order of magnitude, this relation gives a pretty good estimation of the mobility. Now let's move on to the case of thin EDL, which is when the particle size is significantly larger than the ideal thickness. So now consider an insulating particle like this, which has some surface charge and it is immersed in an electrolyte solution. So if you have a particle like this immersed in electrolyte solution, an ideal will form on its surface. So there will be net positive charge that will be attracted towards its surface. Now under the applied electric field, this ideal would lead to an electro-osmotic flow on the surface. So if we look at some simple scaling, we'll say that the electro-osmotic flow will scale as minus epsilon zeta times electric field over the viscosity. Now this is assuming that the particle is stationary and the fluid is able to move, or in other words, for a moving particle we are visualizing this situation in the frame which is moving along with the particle. But in our case the liquid is stationary and the particle is migrating. So in the frame of the stationary liquid, the particle moves in the opposite direction and the particle moves at a speed of epsilon zeta e over eta. So therefore the mobility of the particle is scales as epsilon zeta over eta. So note that we can't use the same model that we had for particles in thick ideal or insulating liquid, where there was a net charge on the particle, because here this whole charge is screened by the ideal. So the motion of this particle is actually due to this electro-osmotic flow. So now we can see that we'll show that actually this relation is not an approximate relation for a spherical particle. This is an exact relation. So the physics is same, so we'll just now prove that mu is actually epsilon zeta over eta when the ideal is significantly smaller than the particle radius. Now to get the exact value of mobility, or to show give a formal derivation of this mobility, what we have is that, so we have this particle and we are applying an external electric field, but this electric field close to the particle is going to change. So at the surface of the particle, the tangential electro-osmotic flow will be given by minus epsilon zeta over eta times the tangential component of the electric field. And we can use this relation still even though we have a curved surface, because the ideal is really thin. So if we zoom in into this region, we'll essentially have a flat surface because our curvature is very small and the ideal thickness is very small compared with the radius of curvature. So we can use the result for electro-osmotic flow over a flat plate locally at all these regions, and therefore we'll get this tangential velocity at component at all points on the circumference of this particle. So now we need to calculate this tangential electric field at the surface, and due to the presence of particle, if we apply an electric field and the particle is insulating, and because the ideal is thin, it screens all the charge on this particle, so the electric field cannot simply pass through the particle. So we need to calculate the electric field. So outside the ideal you have no charge, and therefore we can model the electric field by first introducing a potential, because the quasi-static electric field is irrotational, so we can introduce a potential, and we know that del squared phi is related to the free charge in the liquid, but outside the ideal there is no charge, so we should solve this Laplace equation del squared phi equals to 0. Now at the boundary for the boundary conditions, we note that the ideal is thin and it completely screens the surface charge. So therefore there should be no normal component, or the normal component of electric field should be 0 at the surface of the particle. And in the far field, because we are applying an external electric field, so minus del phi by del x should be equal to the external electric field that we are applying. These are the equations for the potential. Now we will also have to write the equations for the flow. Now at low Reynolds number, we will use the Stokes flow assumption or Stokes flow approximation. So for Stokes flow, we know that outside the ideal there is no charge, and therefore we will have this usual equation for Stokes flow. So minus gradient of pressure plus the viscous term, and we also have, of course, the continuity equation for an incompressible fluid. And the boundary conditions for fluid flow is that the tangential component of the velocity or at the particle surface is equal to the electroosmotic velocity, the local electroosmotic velocity due to the tangential electric field E subscript T. Now, so it turns out that the solution to this problem is actually quite straightforward. So we are not interested in actually finding the solution for the whole solution for the velocity. What we are interested in is finding how velocity is dependent upon the external electric field. So we just want to calculate the mobility. So the idea is that if we try a solution of the form, so let's say that using a trick I try a solution of this form, epsilon zeta times gradient of potential over eta. So if we try a solution of this form and it satisfies these boundary conditions, then if it satisfies, then it is indeed the solution. Now to see that, what I'll do is that we'll use the standard trick of eliminating pressure term from the Stokes flow equation. And to do that, so I'll take this equation and take the curl of this equation, or both sides of this equation, and curl of a gradient is 0, so the pressure term will drop out, and we'll take a curl once again of both sides. And what happens is that we know that curl of some vector field is actually given by the gradient of the divergence of the vector field minus the Laplacian of that vector field. So in our case, so what we'll get is, we'll set by taking the first curl, anyways the pressure gradient term is eliminated, so this equation simplifies to eta times curl of Laplacian of u, and that is equal to 0, and these operators can commute. So what we'll have is that del squared of curl of u. So we'll commute these operators will commute. So what we'll get is equals to 0, and we note that from the incompressibility assumption del dot u is 0, so we are left with a biharmonic equation for u. So this equation takes into account both of these equations. So if we can solve the single equation along with this boundary condition, that is sufficient. Now we see that this solution u equals to epsilon zeta gradient of phi times electric field actually satisfies this equation, and this is straightforward to see. So if you substitute this equation over here, and you see that, so you can write this as del squared of u, and that will be equal to del squared or Laplacian of epsilon zeta gradient phi over eta. And if you take this Laplacian inside, and we know that Laplacian of phi is actually 0, so this is actually again 0. So this form of the solution certainly satisfies Stokes flow equations. All we need to see is that does it indeed satisfy the boundary condition. So if you compare this boundary condition, so if you look at the tangential component of the velocity, it is certainly given by this term over here if we have a solution of this form. Therefore this form of solution satisfies the equation and satisfies the boundary condition. So we have actually obtained the exact solution. So the flow velocity now is given by epsilon zeta gradient phi over eta, and that is the exact solution to this problem. So in the far field, as you go far from this particle surface, so u is given by epsilon zeta, so gradient phi is negative of the electric field over eta, and this is in. So that means if you apply an electric field over a particle which is held stationary, then the flow velocity in the far field is again given by this value when the EDL is very thin. But in our case we have the opposite problem. The particle can move and the fluid is stationary. So the particle moves in the opposite direction, and one would expect that, because if particle is negatively charged, the flow is towards the right for a rightward pointing electric field, but a negatively charged particle will not move along with the electric field, it will move in the opposite direction. So the particle velocity is actually epsilon zeta, or the particle speed with respect to the external electric field is given by this term. So the mobility is the proportionality constant, and therefore the mobility is epsilon zeta over eta. For a negatively charged surface, zeta potential is negative, so the mobility is going to be negative. So this relation or this simple scaling analysis that we provided gives the exact value for mobility, but only in the case when the double layer thickness is significantly smaller than the particle diameter or particle radius. Otherwise we'll use the relation for mobility, which is obtained by balance of the Coulombic force on the particle with the Stokes drag.